So continuing with our prior discussion, we are now going to compute a lower bound and an upper bound for the randomization distribution of Fisher transformed sample correlation coefficients. To do that, I'm going to follow the same principles we've been following all semester. I'm going to plot the Fisher transform of the original set of data, and just in case I've hidden that now, that value is 1.1734. So I'm going to plot that out, twice that value, minus an upper percentile of the Fisher transformed sample correlation coefficients generated through the randomization technique. That's the lower bound right there. I'm going to obtain the upper bound in mostly the same way, 2 times 1.1734 minus a low percentile of the randomization measures, that's 2.4, and Fisher. That gives me the upper bound for my confidence interval. And now what I have to do is I have to take these two numbers, 0.321005 and 1.78639, and I have to undo the Fisher transformation. That is, I have to apply an inverse function to put those numbers back into the appropriate setting of correlation coefficients that are bounded between -1 and 1. So here's how I do that. I'm going to go on ahead and just do those computations right here in this summary table. I'm going to add a formula, and here's the formula that you add. This is how you undo the Fisher transformation. You do the exponential function twice the, let's start with the lower bound, 0.321005 minus 1, and I'm going to divide that by the exponential function twice the lower bound again, plus 1. Okay? That quantity is 0.310415. That's not very different from 0.321005. But what the Fisher transformation will do with the upper bound, the 1.78639, is going to change it a lot. Let's do that computation now. So I'm going to add one more formula here. I'm going to do the exponential function of twice that upper bound, the upper bound of the Fisher transformed randomization distribution. That's 1.78639. I'm going to subtract 1, and I'm going to divide this by the exponential function of twice the Fisher transformed original sample correlation coefficient. I'm sorry, this is the upper bound of our randomization distribution of the Fisher transform measures. And then I'm going to add 1. That gives me a value of 0.94. That's safely underneath 1, so it's a reasonable way to have a confidence interval now, rather than using the switch trick on this data and getting an upper bound that's above 1. So using this technique, which admittedly is a bit complicated, it's not always taught in an introductory course, and it's not examinable in Math 111, we can say that the 95% confidence interval for the true correlation between temperature and chirping frequency is 0.31 to 0.94. Now you might say, how ridiculous. That's an incredibly wide confidence interval, but the fact of the matter is we have very little bivariate data. We have a lot of parameters that are implicitly being estimated to generate the sample correlation coefficient, like x bar, y bar, the sample standard deviation of the x data, the sample standard deviation of the y data. So 15 data points is really not very much to have a very tight confidence interval with or without the Fisher transformation. So this is how you use the Fisher transformation to generate, through randomization techniques, a confidence interval for a true correlation coefficient when the sample size is small and the sample correlation coefficient is quite large.